Sometimes it would be nice to have a certain constraint be fulfilled, but this may not be feasible depending on the parameter values that we use. In cases where one or more constraints would be nice to have but not necessary, we call such constraints soft constraints. This is in contrast to hard constraints, which are a must if we seek a feasible solution. We can illustrate the situation by using the furniture production problem again, which is known from previous videos. The objective is maximize 16 times the number of tables plus 10 times the number of chairs. Tables and chairs are produced out of small parts, 2x4s and 2x2s. Let B1 be the number of 2x4s that we have on stock. The first constraint would be that no more than B1 2x4s can be used for producing tables and chairs. Let B2 be the number of 2x2s on stock, and suppose that for some reason it would be nice to use them all. In addition to that, we may have the idea that it might be nice if tables are sold in a set with B3 chairs. Extra chairs may be produced. And finally, as always, we have x1 and x2 is greater than or equal to 0. Depending on the values of B1, B2 and B3, a feasible solution may or may not exist. Given a model formulation like that, a feasible solution must fulfill all constraints without exception. Suppose now that if all constraints can be fulfilled, we like to have that. But in the case that no feasible solution exists, we are willing to give up the third constraint, let's say. Being able to offer that each table comes in a set with B3 chairs is not important if no feasible solution can be achieved otherwise. In other words, the third constraint would be a soft constraint. How can we express this? Well, the third constraint is a greater than or equal to constraint. If we subtracted a large enough value from the right-hand side, the third constraint will always be fulfilled. So basically, we can introduce a new decision variable, let's say y3, and subtract it from the right-hand side. y3, of course, should be non-negative. A formulation like this would not make much sense. This is just a very complicated way to delete the third constraint from the model, because we can always choose an arbitrarily large value for y3 to fulfill the third constraint. Make sure to understand that a constraint that can always be fulfilled without any interaction with the rest of the model is as good as no constraint and can be deleted from the model. So how can we make the third constraint become a soft constraint that is deleted from the model only if there is no other way to find a feasible solution? The trick is to use the objective function. We face a maximization problem. If we subtract a large value from the objective function value if and only if y3 is positive, we have an incentive to assign the value 0 to y3 unless there is no other way to find a feasible solution. Let M3 be a large positive number. M3 can be seen as a penalty term. It lowers the objective function value if y3 is positive. Since we want to maximize the objective function value, we would prefer to have y3 equal to 0. A positive value for y3 would only be chosen if there is no other solution. Note that if we had a minimization problem, we would not subtract the penalty term, but we would add it instead. M3 is a positive parameter and it is specific to the instance. Its value must be chosen carefully. As a rule of thumb, it should outweigh the objective function values of feasible solutions of the original model formulation. Now let's turn to the first constraint. Suppose that we want the first constraint become a soft constraint. In essence, we do the same we did before. I suggest that you give yourself a try and pause the video now. The important difference is that we face a less than or equal to constraint now. Hence, we would have to add a large value to the right-hand side to make sure that the constraint is always fulfilled. Let's use a new decision variable, y1, to do the job. Again, a penalty term, say m1, in the objective function. Make sure that a positive value is assigned to y1 if and only if there is no other way to ensure feasibility. Note that the procedure shown is a technical modeling trick to make a constraint become a soft constraint. If you changed the story a bit so that extra 2x4s can be bought and y1 represents the number of 2x4s that are purchased, and the parameter m1 would stand for the price to be paid for each extra 2x4, the model would look very much alike. But then, the first constraint would be no soft constraint but a hard constraint to be fulfilled. The key difference is that m1 would be no very large number that can be arbitrarily chosen as long as its value is large enough. m1 would be a reasonable price instead. Finally, let's have a look at the second constraint, which is an equality constraint. How can we make this a soft constraint? I recommend to think about it by yourself and pause the video now. The way to do that is to combine the two approaches just seen. The left-hand side and the right-hand side may deviate from being equal if violations of the equality constraint should be allowed. This time, both directions are possible. A straightforward approach would be to use two new decision variables, say y2 plus and y2 minus, as follows. The objective function would have to be modified where m2 plus and m2 minus are penalty terms. A final remark seems to be in order. In this example, all constraints became soft constraints. This was done for illustrating the approach for less than or equal to, greater than or equal to, and equality constraints. In many applications, we find that only a few constraints should be soft constraints.